Counting is the most fundamental way of quantitatively analysing data. It is also one of the earliest abstract tasks we learn, yet generic counting still hasn't been automated. There has been substantial work into class-specific tasks, and because of that we have accurate single-purpose counters for things like cells, people and cars. However, we need large amounts of data and to retrain the model for every new class. Class-agnostic counting, which emerged in 2018, addresses this problem. In class-agnostic counting, inference time classes are not seen during training. This creates a much more general counting tool. Until recently, class-agnostic counting has been based around the use of exemplar images. A user specifies a set of exemplars from the query image, and these are matched to other areas of the image to generate a count. Obviously, people do not require exemplars to count. I could give you an image of 25 objects you have never seen before and ask you to count, and you'd be able to do it. You could also do this even if there are multiple kinds of object present in an image. Unlike other methods which require exemplar images on top of the query image to define the type of object to count, our method produces accurate results from only the query image. Given this is now an unguided task, it is non-trivial for a user to understand what has been counted. So we find examples from the image to explain each count. This effectively flips the exemplar-based paradigm on its head. Our paper has three main contributions: MCAC, a multi-class, class-agnostic counting dataset; ABC123, an exemplar-free, multi-class, class-agnostic counting method; and the introduction of the idea of example finding to exemplar-free counting. For accurate class-agnostic counting, you need datasets with a wide variety of classes, but no overlap between the classes in the training, validation and testing splits. Prior to this work, there was one class-agnostic counting dataset, FSC. FSC has limited labeling. It's single class with only one labeled class per image, only point annotations, a few bounding boxes per image, and arbitrary distinctions between which instances should and should not be included in the count. To facilitate work into multi-class, class-agnostic counting, we introduce MCAC. Images in MCAC have multiple classes of object, but these classes are mutually exclusive between the dataset splits. MCAC is a 3D rendered synthetic dataset. This allowed us to gain accurate pixel-wise annotations, complete class hierarchies, and accurate measures of occlusions. We think the occlusion measurement is especially important as it allows you to precisely decide how much of an object is needed in a scene for it to be included in the count. Our method, ABC123, is built around the intuition that counting is a simple, though not necessarily easy, task. You identify what could be worth counting, and then where repetition occurs. Transformers are perfectly suited to this task. Their use of attention is inherently finding repetitions, even where instances are spatially distant. Transformers have also been proven to excel in detection tasks. As such, we're able to keep our pipeline as simple as possible. We generate predicted density maps using features from a VIT backbone, which are upsampled using a convolutional counting head. During training, we match these predicted density maps to their associated ground truth density maps and use a pixel-wise L1 loss for training. We can integrate the predicted density maps to find their counts. To find representative examples of each counted class, we first find points that have a high activation in only the relevant density map, avoiding the other classes. To ensure the user understands the range of each counted class, we then take a set of points from each class which have diverse feature representations. These points are used as seeds to generate segmentations from the original image. Here, you can see the predicted density maps for a given image. It is not particularly easy to interpret what has been counted. However, the found examples clarify the generated counts. We also present results from two other images with 4 classes to count. ABC123 is cross-domain generalizable. Here you can see results of ABC123 trained on only the synthetic data of MCAC and then applied to photographic images. ABC123 trained on MCAC achieves state-of-the-art results on both MCAC and FSC. Our paper, code, and datasets are available online.